Okay, so what we're looking at here is an example from the 2010 exam of a parametric equations problem. And even though this problem's a little bit older, you'll notice that this particular type of problem pretty much looks exactly the same regardless of when it was given. So let's go ahead and just jump in and see what's happening in this problem. So we've got the velocity vector of a particle moving the xy plane has components of, and it gives us dx dt here, and then it gives us dy dt here as well. And then it gives us a time interval from 0 to 1.5. Then it also says at time equals 0, the position of the particle is negative 2, 3. So it's almost like they give us our initial position here, and they give us the velocity vector, not written just as individual components. Not that big of a deal, okay? So letter A on this problem says, find all the values of t at which the line tangent to the particle is vertical. Now what we have to realize in this problem is that if we want the if we want the slope of a tangent line, we have to find dy dt divided by dx dt, and that'll come into this problem a little bit later. But anytime the tangent line is going to be vertical, that's when dx dt is going to be equal to 0. So what we're doing in this problem is we're taking dx dt equal to 0, and so we do have to remember that we're looking at this interval from 0 to 1.5. So I look at dx dt where that's equal to 0, and that happens at two different places, okay? It's at one, we just graph it, we find out where it crosses the x-axis. One place is at 1.253. The other one is at 1.144. So those are the two places where the tangent line is going to be vertical. That's the answer to letter A. Letter B wants us to write an equation for the line tangent to the path of the particle at time equals 1. Now this one's a little bit tricky just because, like, I have to go find dy dt over dx dt. That part's actually the easiest part of this problem. So dy dt, dx dt, what I'm going to do is I'm going to plug in 1 into both of those equations because I already have those. And when I do that, I get 0.863. The problem is if I'm writing the equation of a line tangent to anything, I've got to go y minus y1 equals m times x minus x1. Usually the hardest thing to find is the slope, but this time it's the easiest thing to find. And the reason for that is I don't know y1 and x1 at time equals 1. I know y1 and x1 at time equals 0. So in order to find both y1 and x1, we have to use our formula of taking our initial position plus our displacement for each of the y value and the x value. So if I'm looking for x1, I would take negative 2 plus the integral from 0 to 1, because that is the x-coordinate at time equals 0. So I go negative 2 plus the integral from 0 to 1 of my dx dt. And when I do that, what I get is 9.315. So that's going to, oops, this is supposed to be x right here, not a y. So that is my x1, 9.315. Then I have to do the same thing for y1. So I take my initial condition plus the integral from 0 to 1, but we're going to use dy dt this time instead of dx dt. And that gives me, when I put that in, 4.621. So my y value is 4.621. So there's my equation of my tangent line at that particular time. Again, why this one's so tricky is because we don't know the position of the particle at time equals 1 initially. We had to find both of those. Luckily for you, if you were taking this problem, that would have been worth 4 points. Letter C just says find the speed of the particle. The way that we do that, the definition of speed is the square root of dx dt squared, when we plug in 1, plus dy dt squared. So I put all that right there as my speed equation. Then I just plug in time equals 1, and when I put that into my calculator, I get 4.105. Again, just applying the definition of what speed is on this particular problem. And then letter D says find the acceleration vector. Well, what that means is we have to take the derivative of each of these and then plug in 1. So when I take the derivative of the x component of the velocity, I get negative 28.425. And when I do the same thing for the y component, again, I'm just using math 8 on my calculator, I get 2.161. So my velocity vector, if I want to write it formally, looks like this right here. And again, hopefully all of that made sense. That one was a little tricky in a couple places. That's probably one of the harder questions I've seen when it comes to the parametric equations. But at the same time, it's not that bad. Hopefully all of that made sense. That letter B was a little rough, but again, hopefully that kind of makes sense. If you have any questions about this one, please let me know.